Swayam Prabha. Digital India. Educated India.
Okay, so let's continue our discussions related to the course Introduction to Electronics. So today we start with a new topic, which is semiconductors, and then we'll go on to semiconductor devices such as diodes and transistors, and then circuits made out of them. And in the very beginning, we had said that this is the outline of the course here. There are 3 modules. Tools for circuit analysis, analog circuits, and then digital circuits. So we start a discussion related to the second module today. All right, so semiconductors, as the name indicates, are a class of materials whose conductivity lies in between metals and insulators. So if we look at insulators, let's say glass or diamond or nylon, we see that their conductivity is very, very low, 10 power minus 10, minus 12 Siemens per centimeter here. And on the other hand, we have metals, silver, copper, iron, whose conductivities are very high, 10 to the power 6. And semiconductors lie somewhere in between. You can see here with a conductivity of 1 here, and even with a conductivity of 10 power minus 5. Okay, so there's a fairly large range of conductivities which lies in between those of metals, which are highly conducting, and insulators, which have very, very low conductivity here. And so those are a class of class of materials which lie, and one of the most common semiconductors is silicon here. All right, so before we discuss semiconductors in a little bit more detail, this is an interesting quote from a well-known science fiction author, Arthur C. Clarke, and I think it was made somewhere in 1960s, that any sufficiently advanced technology is indistinguishable from magic. So let me illustrate this particular point here. So the point is that semiconductors have allowed us to perform magic. Almost things which will look like magic to previous generations or generations which had not seen electronics. To them, the kind of things that we can do with electronics would appear as magic. Okay, so let me illustrate that. So magicians use a hat, and they pull out interesting things out of hat. They pull it out of thin air. But in our case, in this hat, I'm going to add something here, which is sand. So I'm going to add sand here, and I'm going to take a wand, and like a magician, of course, swing this wand here. And what will come out of this hat is not a rabbit, but something that is very dear to all of you, is your cell phone. Right? So from sand to cell phones. So how does that happen? So this is nothing short of a magic, that you can start from sand and you can create a device like you can get a device like a cell phone on which you can listen to your favorite music or watch your movies or even listen to this particular lecture. All right, so how is this magic trick performed? So let's look at that. Behind all magic tricks, there is actually science. So how is this magic trick actually performed? Okay, so let's start with sand. So here is sand. And so the sand that we are talking about is a special kind of a sand. Not every sand will have. So the sand has these small crystals of quartzite. And quartz is nothing but silicon dioxide, crystal of silicon dioxide here. All right. So we take sand, which has a high proportion of quartz in it, quartz crystals in it. And we start from there. And we need to extract silicon from there, right? So we start from quartzite here, this powdered form of sand here. And we react it with carbon. And so we get silicon out of it. We call it metallurgical grade silicon. It's not very pure, 95 to 98% pure here. And this is what we end up with. But this kind of a silicon is we cannot make our devices, our circuits on this kind of a silicon. It's not pure enough. And so what we do is we take this metallurgical grade silicon here and we refine it. And so you can read a few details about it. The 60 tons of quartzite, which contains about 45% silicon, and 25,000 tons of charcoal are required to produce 28,000 tons of silicon, 13 megawatts of electricity to produce 1 ton of silicon. And the cost of electricity itself represents 40% of the market value of silicon here. So anyways, so we take quartzite, we react it with carbon, and we get silicon. Not a very pure silicon, but we get a metallurgical grade silicon here. So we need to purify it. So what we do is we basically take this metallurgical grade silicon, react it with HCl, and we get trichlorosilane here, and which is a gas, and which can be in the gaseous form. And we use a vapor deposition. We break it up into silicon, and we use vapor deposition to produce a pure form of silicon. A pure form of silicon, but it's polycrystalline. When we deposit it on a surface, we get not a single crystal of silicon, but we get a polycrystalline silicon, many crystals of silicon oriented in random directions here. All right, so we get a polycrystalline, but we get electronic grade because of this vapor deposition process here. We get very pure silicon here. Next, what we do is we take electronic grade polysilicon and we have to convert it into a crystal of silicon here. So basically we melt this polygrade silicon here. We dip a small seed of pure silicon crystal, a seed, and we pull it out. And we pull it out and you get these cylinders of silicon crystal here, right? So you have this big several feet long crystals of silicon. These are pulled out of this particular melt here. The melt is made out of electronic grade polysilicon here. And then what we do is we slice it up. We slice it up into thin wafers here. So these thin wafers that you see here, these are about 400 micron thick wafers here. So these are single crystalline wafers, about 400. And you can, depending on the diameter here, the kind of growth or the crystal that you pulled out, they can be these wafers of different dimensions. 300 mm or 200 mm diameter are common dimensions of this particular wafer here. So that's how we end up with the wafer or the substrate on which all the devices, all the circuits, all the ICs are made here. A very thin 400 micron thick crystal of silicon here. And the journey, of course, begins from the sand here. And because of all these purification processes that you see here, sand may be very common, but the final silicon wafer is quite expensive. $1,400 per kg is like one number that is there here. A wafer, a silicon wafer with a diameter of 200 mm may cost about $45. This is an old data, $45 in 2006 here. All right, so this is so from sand we have obtained a thin slice of silicon. Note that it is pure crystal and the purity level is extremely high. It's one of the purest materials that you can get anywhere on the planet here. And so on this wafer is where we make our transistors. A MOSFET that we have seen earlier. On this wafer we can make MOSFETs, and we'll see towards the end of the lecture very quickly how something like that can be made here. And we make not just one MOSFET, but we make hundreds of thousands or millions or even billions of transistors. And those transistors, the circuits that we make, those are packaged, which is shown here, packaged integrated circuits. And these integrated circuits, and then along with various, several ICs, along with maybe resistors, capacitors, they're all integrated on a PCB, a printed circuit board, an insulating board on which all these things are soldered on. And you may take several PCBs, and you may interconnect them to make your final cell phone here. So there are many, cell phone is a fairly complicated thing. There are amplifiers, there's a microprocessor, there's a memory, there is a audio system with digital to analog and analog to digital. There's digital signal processing. So all kinds of things that are there. And each one is being performed by an IC here. So there's an IC here, there's an IC here. So that's one PCB, there's another PCB, and several PCBs may be integrated together to create the final system here. So the electronics revolution that we have talked about is a revolution from sand to mobile. And in very brief, we saw what the journey is, how we obtain the final system starting from sand here. All right, so let's look at this in a little bit more detail. So silicon, we said, is a semiconductor. And semiconductor, meaning conductivity lies somewhere between metals and insulators. But more importantly about semiconductor is that its conductivity can be altered and controlled. See, if you take a metal, if you take copper or silver, or the conductivity is 10 to the power 6, you can't do too much to the conductivity. It's already too high. And maybe a little bit you can alter it, but there's not too much control over it. Similarly, if you go to an insulator, the conductivity is very, very low. And it hardly passes any current, so you can't do much with that also. You can't do any interesting things here. But with semiconductor, well, its conductivity can be controlled, can be altered and controlled here. And this is what allows us to control current. The foundation of electronics is that it allows us to control electricity. And we said electricity is a very useful form of energy. And semiconductors are the tools through which we control electricity. And the foundation of it, why are we able to control the conductivity, is one of the things is the phenomena of that we can add impurities to them to change their conductivity by a large magnitude. So let's look at that in a little bit more detail here. All right, so let's look at silicon. Silicon, we are all familiar, lies in this group 4 here, atomic number of 14. And so its electronic structure is 1s2, 2s2, 2p6 and all that here. And it has a complete shell till 2 and 4 electrons in the outermost shell here. And these 4 outer shell electrons, they form 4 covalent bonds here. So that's how we get a crystalline structure of silicon here. Okay, so this is a tetrahedral structure here. And so all electronics is being done on crystals of silicon, and this is the unit cell of silicon here, and you can see the lattice constant is 5.43 angstrom here. So that's the structure of silicon. Now the electrons in a crystal, in a silicon crystal, occupy bands of energies. So you've seen, we're all familiar with that in an atom the electrons exist in these discrete energy levels, 1s, 2s, 2p and 3s and 3p. Now, when you form a crystal, what happens is these levels which belong to, let's say, one atom, they interact with the levels belonging to another atom. And as a result of which, these single discrete levels, they expand into bands like this here. So we get bands of energies here. So we get a band of energy maybe corresponding to 1s, band of energy corresponding to 2s. And as each one of these levels, they expand into a band, there is a mixture that occurs between maybe 2s and 2p or 3s and 3p. So bands merge with each other, overlap with each other. So all kinds of interesting things happen. So from a simplified point of view, all these crystals, all these crystalline solids have these bands of energies. Unlike a atom where you have discrete levels, you have bands of energy levels that are there here. And for a semiconductor such as silicon, so you have bands of energies that are there here. And in gray here or bluish here, what we are seeing is bands which are completely full with electrons. Just like you have a level, 1s level is completely full, 2s level is completely full, 2p is also completely full. So similarly, we have these bands which are completely full of electrons. And so these are complete, the whole band is full. And then we have a band which is completely empty here, For example, if I were to take a level like 3D or 4S or whatever, they are completely empty, right? So similarly, we have bands which are completely empty. So in red are completely empty bands. There's nothing here, no electrons here. And these are all possible states that are there are completely full here. So these are full bands here. Okay. So completely empty and completely full. So that's the picture of silicon. If we think of silicon at, let's say, 0 degree Kelvin, when there is no extra energy available to promote an electron from one place to another place. So at 0 degree Kelvin, this is the state of silicon. And this is the state of all insulators also. All insulators will also be like this. There'll be a bands which are completely full, and then there are bands which are completely empty. All right. So the bottommost empty band. So these are the empty bands in red. The bottommost empty band is what we call as the conduction band. We'll see why this is called conduction band. And the topmost filled band, so these are all filled, but the topmost band is interesting for us. It's called the valence band here. So out of all the bands that are there, these are two special bands. Valence band, the topmost filled band is called valence band. Filled band where? At 0 degree Kelvin. At 0 degree Kelvin, this is completely full. And at 0 degree Kelvin, this is completely empty here, right? So that's the conduction band here, and that's the valence band here. So you may be wondering that, okay, so I have all these electrons that are there here and here and here. And if I apply electric field, these electrons should move and contribute to current. But it turns out this is an interesting thing that happens when electrons exist in bands like this, is that although there are a lot of electrons in this band and this band, when you apply current, these electrons are useless. They cannot give rise to any current here. So that's an interesting point to look at. Electrons in a completely full band cannot contribute to current conduction. That's an important point here. So let's look at a band here. So a band of energies, okay, and it's completely full. Now, completely full. So now if you take an electron and let's say you apply an electric field, for this electron to respond to this electric field, there's a force that acts here. The electron will move. For this electron to respond to this electric field, it has to gain energy from the field here. It has to move. But now note the electrons that you see here. The electrons that you see here, where will it go? If I focus on this particular electron, if it has to respond to the electric field, gain energy, where can it go? There is no place to go anywhere in this particular band here. Okay. Similarly, I take any electron. There is no place for this particular electron to go here. And if you're thinking that this electron can exchange place with this, well, then that will also not contribute to current, right? One electron goes in one direction, two electrons which exchange their places, they're moving in opposite directions, and that will also cancel each other. Anyway, so the point is that when we have a full band, the electrons cannot gain energy from the field, the electrons cannot have any net motion, and therefore a full band will not contribute to any current. All right, so the picture of silicon crystal at 0 degree Kelvin is following. We have this conduction band and we have this valence band, and there's an energy gap, and different semiconductors will have different energy gap, and we call it a band gap between the top of the valence band and the bottom of the conduction band. The energy gap that is there here is what we call as the energy gap. So that's 1.12 electron volt here. All right, so this is the picture that we have. So now you can see why silicon at 0 degree Kelvin is an insulator. These two are obviously empty. So if I apply an electric field, these two bands, they don't have any electrons, so obviously they cannot carry current. And these bands are all full. And we just said that a band which is completely full of electrons cannot carry current here. So even though there are a lot of electrons here, a lot of electrons here, a lot of electrons here, none of them can contribute to current. And therefore, when you apply an electric field to silicon at 0 degree Kelvin, there will be zero current. It's a perfect insulator. Okay. Now you may be wondering, well, is it possible that I can take an electron from the valence band to the conduction band here? Well, we are talking about 0 degree Kelvin, so there's not enough energy, thermal energy available to do that. And the typical electric fields that we apply are not enough to rip an electron off and put it into the conduction band here. So that also is, this kind of an ionization process is also not likely to occur under typical fields. So that also doesn't happen here. And that's why a silicon crystal at 0 degree Kelvin acts as a perfect insulator. So this is something that doesn't happen. Okay. Now let's picture silicon at room temperature, 300 degree Kelvin here. So now the electrons have, some of the electrons gain enough energy from the ambient, from the thermal energy which is available, and they're able to cross over this energy gap here and arrive at this particular place in conduction band. And when the electrons leave and arrive in the conduction band, they leave behind these vacant spaces here. Thus, some of these states are no longer filled, and these vacant states, unfilled states, is what we call as holes here, missing electrons here, right? So now these things will happen from the valence band here. See, the energy, thermal energy, is not enough to take an electron from here and then promote it to something like conduction band here. So these bands typically remain all completely full, and it's only some of the electrons from the top of the valence band, close to top of the valence band, who are able to make it over to the bottom of the conduction band. Similarly, from here, electrons from here to go to another band, which is even further away in energy, that is also highly unlikely. It doesn't occur here. Okay, so when you go to 300 degree Kelvin, what you find is that the valence band is no longer completely full. There are few empty states there. And the conduction band is no longer completely empty. There are few electrons over here. And then things become interesting. So note that this band obviously is completely empty even at room temperature, or you go higher than room temperature, let's say 90 degrees Celsius or whatever. These will remain empty. And therefore they are useless from the electronics point of view. They don't contribute to current. Similarly, the deeper bands in energy, these are also, they will remain completely full, and so they are also not of any interest to us. A completely full band will not contribute to current, so it's not important from the electronics point of view. So the only two bands which are of interest to us is the valence band and the conduction band. And even there, all the action occurs at the bottom of the conduction band, and all the action, interesting things happen at the top of the valence band here. Okay, so it's only at the top of the valence band and the bottom of the conduction band that interesting things happen here. There are missing states here, and there are electrons present at the bottom of the conduction band here. So conduction band has few electrons, valence band has few empty states. And now if you apply electric current, or if you apply electric field, these electrons can move here. Obviously in the conduction band, they have plenty of states that are available, so electrons can gain an energy. So note that we have very few electrons in the conduction band. Now if you're wondering how many states are there in the, let's say in a typical band here. So if we take silicon, the number of silicon atoms per centimeter cube is about, let's say, 10 to the power 22. That's the order. And so there are roughly 10 to the power 22 states per unit volume. That's the number of states here. And typically the number of electrons in any of these semiconductor devices and all that we are talking about is much, much less than 10 to the power 22. Okay, we are talking about a typical number, let's say 10 to the power 16 or 10 to the power 17 per centimeter cube. And the number of states is 10 to the power 22. So which means that the conduction band, you can also see, is practically empty. There are few electrons, but most of these states are empty. And therefore, if you apply an electric field, well, the electron can respond to the electric field. The electron can gain energy from the field and go to a higher state. There are plenty of states which are available here. Okay, this electron can respond, this electron can respond here. So conduction band electrons are free to move in whatever direction they wish. And therefore they can respond to electric field and they can give rise to current. All right, so that's why conduction band is important for us. The electrons in the conduction band, they can move and in response to electric field and can give rise to current. And these electrons are, they're like, we call them as free electrons. They can move from one place to the other place in the conduction band here. Note that when we draw a level like this here, this energy level like this here, this energy level spans the entire crystal. Okay, this energy level doesn't belong to a single atom. This energy level in a band belongs to the entire crystal. So this electron is free to move anywhere in the crystal. Okay, This electron is also free to move anywhere in the crystal. This electron is also free to move anywhere in the crystal here. Okay. Now, valence band is more interesting. We have shown a case where valence band is practically, note that the number of states is again of the order of 10 power 22. A few electrons, 10 to the power 16 per centimeter cube, have gone to the conduction band. So the number of empty states is about 10 to the power 16 or 10 power 17 per centimeter cube empty states here. Very few empty states. Most of these electrons are full. But now the electrons in the conduction band can also move here. Note that the electron can move. The electron can go and take the place of the missing state here. So this energy level here has its full electrons, one spin up and one spin down, so it's completely full. But now this becomes empty here. And an electron from here could jump into this particular state here, and now this becomes empty. So you can see that electrons are able to move now. Electrons can move now, and if they can move, they can contribute to current conduction here. So there's a net movement of electrons contribute to current conduction here. So let's look at a simplified picture then of how a electron may move here. So electrons in general are moving anywhere in the crystal here. All right, so electrons. Now, why did I show that the electron moves and then we are showing that the electron gets scattered? The electron moves and then gets scattered, and it's moving in some random directions here. And scattering occurs because in a crystal at room temperature, the silicon atoms that you see here are not in their equilibrium position. The silicon atoms are vibrating. They're vibrating, and these vibrations are what causes the electrons to scatter. So an electron may start at a place and doesn't continue to move in a straight line, but it gets scattered due to the vibrations here. Now, these phenomena are complicated. They require quantum mechanics to explain them in detail, and therefore we are painting a very simple picture. But the concept, basic concept is that because the silicon atoms are not in their place, they're vibrating. The electrons, as a result of these vibrations, the electrons get scattered. They move a certain distance and then they get scattered. Then they move a certain distance, then they get scattered. So electrons are executing some kind of a random motion, as I've drawn here inside the crystal here. And just like a molecule in a room is executing a random motion, similarly an electron inside a crystal is executing random motion, and there's no net movement of any electron. There's no preferred direction, which is obvious that, and therefore when you don't apply any electric field, there is no net movement of the electron. There's no current that is flowing here. The picture of a hole is, sometimes we picture a hole as a missing electron here. And as I said, quantum mechanically, the picture is you require that to really understand the concept of a hole and the movement of a hole. But simplified picture is there's a missing state here, and the electron can move into this missing here, and thereby you can see the movement of the electron is you can think of movement of an electron same as if the hole has moved over here. The hole which was over here, now it has moved here. So in a valence band, instead of thinking about movement of electrons, we can equivalently think of movement of holes. Similarly, there's a vacant space here in the neighborhood. Let's say the electron may move here, and now the electron moving like this here, this electron can be thought of as a hole moving to this particular place here, right? So note that what has happened is 3 electrons have moved. This electron started from here and moved here. Then this electron started from here and moved here. And this electron started from here and moved here. So now there's a movement of 3 electrons. And in effect, what has really happened is that the missing state has moved in this particular place here. So that is why the concept of a hole is used. Instead of talking about movement of 3 electrons, which is far more complicated, the movement of these 3 electrons is in effect same as movement of a hole from here to this particular point here. Movement of a hole in this. So we just said in valence band there are almost to the of the order of 10 power 22 electrons, and number of holes is maybe 10 power 17. So instead of talking about the complicated movement of all those large number of electrons, we can just talk about the movement of the holes here. Just the movement of this hole from, so instead of 3 electrons moving like this, it's much simpler to talk about a hole which started from here, went here, went here, and went here, and arrived here. So instead of 3 electrons, 1 hole here. And the net effect of the current carried by these 3 electrons is the same thing as this hole which started from here and ended up here. And the net effect is the same as this particular hole, provided we assign a positive charge to it. So the motion of valence band electrons is equivalent to motion of vacant states called holes here. Again, as I said, we are painting a very, very simple picture of what is really happening here. So what we are saying is the net movement of valence electrons here, valence band electrons here. These are very simple equations. So what we are saying is the net movement of valence band electrons here is equivalent to the movement of holes over here. So what we are saying is that we can model the current flow in valence band in terms of the movement of holes, number of holes, which is, or number of vacant states, or number of holes is P here. And provided we assign them a positive charge. So if you go back to the previous picture, these 3 electrons, they moved in this particular direction here, and the hole moved in the opposite direction here. So the net movement of those 3 electrons to the left is equivalent to the movement of hole to the right here, right? So that's why we are assigning it as a positive charge here, opposite direction here. So what we are trying to do is tell is that in a semiconductor, at any reasonable temperature away from 0 degree Kelvin, the current is carried by electrons in valence band, but we can model them as current carried in terms of holes that are there here, provided we assign them a positive charge. Okay, so current in a semiconductor is carried by electrons in conduction band and holes in valence band here. And so the point is that the movement of all the electrons in the conduction band is equivalent to the movement of holes in the valence band here. So you can think of electrons in conduction band, or equivalently you can think of holes in the valence band here. And it's much simpler to talk in terms of holes that is there here. Okay, so that's why when we talk about current conduction in semiconductors, whenever we talk about electrons contributing to conduction, we always mean electrons in the conduction band. And whenever we talk about holes contributing to current conduction, we talk about holes in the valence band here. So think of holes as quasi particles carrying a positive charge. So pure semiconductor is interesting. It has conductivity which varies with temperature, and you can make, for example, thermistors, temperature dependent resistors out of them. You can make photoconductors. You can do interesting things with the pure intrinsic semiconductor. But most of the semiconductor devices that are there, for example, diodes and transistors, they employ impurities. And the impurity is used to alter the conductivity of the silicon here. So adding small amounts of impurity can drastically alter the number of electrons and holes in a semiconductor here. So before that, if I take semiconductors such as silicon, and if I look at it at room temperature, 300 degree Kelvin, in a pure semiconductor, the number of electrons is equal to number of holes, because the electrons come from the valence band. So the number of electrons is equal to number of holes. And the order, the number of electrons and holes in silicon at room temperature in a pure silicon is 10 to the power 10, is of that particular order. Precise number, if you're looking at it, is about 1.45 multiplied by 10 to the power 10 per centimeter cube. So in 1 cubic volume, 1 centimeter cube of silicon, they are going to be 10 to the power 10 number of electrons and 10 to the power 10 number of holes that are there here. Now, if you want to alter the number of electrons and holes, well, you can do that by adding impurities. And that process is what we call as doping. So if you want to increase the number of electrons, so silicon belongs to group 4. So you go to a impurity which lies in group 5. So group 5 will have, as you know, will have 5 electrons in the outer shell, so has an extra electron. And so that is going to increase the number of electrons if you add it to the semiconductor. On the other hand, if you go to group 3, so that has a lesser number of electrons, so that would help in creating holes in the valence band here. So addition of group 5 element impurity to silicon will increase electrons, while group 3 will reduce the number of electrons or increase the number of holes in the system here. Okay, so for example, phosphorus is a common impurity atom, arsenic is a common impurity atom, boron, for example, is a common impurity atom that is added to silicon to increase the electrons or holes. So that process is called doping, right? So in this case, for example, we've added a phosphorus atom here, and phosphorus has this extra electron that you see here, and thereby it increases the number of electrons in the system. And when you have number of electrons which increase in the system, we call that semiconductor as an N-type. N is the number of electrons. Electrons carry negative charge, so we use the symbol N to denote number of electrons per centimeter cube in a piece of silicon, and we use P for positive charge, number of holes that are there per centimeter cube. So when you add a N-type impurity such as phosphorus or arsenic, what you do is you end up increasing the number of electrons. Note that number of electrons, they increase, and you end up with a semiconductor which we call as N-type. N is greater than P. And on the other hand, if you add a impurity such as boron, then you end up increasing the number of holes that are there in the semiconductor, and P, number of holes per centimeter cube, becomes larger than number of electrons in the semiconductor here. And you get what we call as a P-type semiconductor. So you can, if you take an intrinsic silicon, then N equal to P. Number of electrons is equal to number of holes. You can make a semiconductor N-type by adding group 5 impurity. You can make a semiconductor P-type by adding a group 3 impurity. And the more the impurity you add, the stronger the semiconductor becomes of N-type here. And what is the typical level of impurity that we add? Well, we can add anywhere from, let's say, 10 to the power 12, 10 to the power 13 per centimeter cube to anywhere maybe 10 power 18, 10 to the power 19. Typical doping may be 10 power 16 or 10 power 17 per centimeter cube. Now, these all, of course, depend on applications, depend on what you're trying to create. So you can have a high level of N-type doping or a low level of P-type doping, all of those things that you can do by adding it here. Now, this is an important point. We have been saying that the number of silicon atoms per unit volume is about 10 power 22, 4 times 10 power 22. Impurity concentration, I just said, we add about 10 power 17. Now, 10 power 17, and each one of those, this is acceptor type impurity, group 3 impurity. And so what we are doing is, if you take these numbers, you're replacing one silicon atom. You're substituting one silicon atom. 1 in 400,000 silicon atoms is being substituted by boron. So the level of impurity that we are adding is very, very small, 1 in 400,000. And so the point that is being made is very small amounts of impurity atoms can cause a drastic change in electrical property of a semiconductor. Why are we saying that? Well, we said that, for example, when you add one boron atom, the boron atom has one less electron and is going to create a hole corresponding to that one boron atom. So 10 to the power 17 boron atoms are going to create about 10 to the power 17 holes in silicon. Now these holes will contribute to conduction. Now how many holes are there in intrinsic silicon, in absolutely pure silicon? 10 to the power 10. So when you add 10 to the power 17 holes, 10 to the power 17 boron atoms, you're going to increase conductivity by an order of 10 to the power 7. Because compared to 10 to the power 10, 10 power 17 is 7 orders of magnitude higher. So you're going to increase the conductivity by 7 orders of magnitude. But what is the percentage of impurity that you've added? 1 in 400,000. Very, very small amounts of impurity are causing orders of magnitude change in the conductivity here. And it's one of the reasons that you see here is why, even though sand may be plentiful and dirt cheap, electronic grade silicon is so expensive. We need highly pure silicon. If you take silicon which already has impurities in it, then if it already has impurities of the order of 10 power 18 and 10 power 19, then your addition of boron and phosphorus and all that is not going to make a difference to that silicon. And it's one of the reasons why semiconductors took some time to become common, because when people started working with semiconductors, the semiconductors that they had was not very pure, and it had a lot of impurities to begin with, and different scientists and different researchers would get different conductivities, and it was very hard to work with silicon. And real progress in silicon started only when people could purify silicon to a very high degree. So once you get a very, very pure silicon, then you can add impurities in controlled amounts, and then you can study what is the effect of that impurity. You can create devices. And that's why silicon in extremely pure form is very, very important. And it's one of the purest material on earth. Okay. And it's also, there are other reasons also. It's also for that reason that when we do processing of silicon, when we try to make devices on silicon, we do it in an ultra clean room. Any impurity which gets into silicon, which is unwanted, will play havoc with the with silicon, will play havoc with its characteristics. And therefore, there are other reasons also. The processing of silicon then takes place in what we call as highly clean rooms, where people are dressed up in these suits so that even when you inhale, when you exhale, you are exhaling a lot of particles, and you don't want those particles to get into your silicon because they're going to alter its property here. So we are talking about highly pure material, and any impurity which is added in very, very controlled amounts in ppm levels here. And if you're wondering how clean is this particular room, so let me give you this particular data here. So let's look at cleanliness of a room may be measured in terms of how many particles of a particular size are there per meter cube. So let's focus on this particular column here. So this column says that particles of size greater than 0.5 micron in 1 meter cube. 1 meter cube is 35.2 feet cube here, okay? So 1 meter by 1 meter by 1 meter here, right? So in a typical room, ordinary room, there are 35 million particles per meter cube whose size is equal to or greater than 0.5 micron. That's a typical room that is there here, 35 million particles. Now the processing that we are doing, silicon processing that we are doing it in what we call as class 100 clean room. There are clean rooms of different class. This is class 10 room, this is class 100, class 1000 here. So class 100 kind of a clean room, which means there are only 4 particles of size greater than or equal to 0.5 micron per meter cube here. Now you can imagine 4 particles versus 35 million particles here. So how clean, when we call it a clean room, you can compare the cleanliness in terms of the particle sizes here. 4 particles per meter cube versus 35 million particles per meter cube here. Okay. All right, so that's the kind of a cleanliness, either class 100 or class 1000. So all silicon processing is done in class 100 or class 1000, that kind of a thing. Mostly in class 100 or even better kind of a processing. And that's why the processing is done in an environment like this here. Okay. So it's a great technical challenge to maintain that kind of a cleanliness that is there here, with a lot of use of positive pressure, HEPA filters, all kinds of things that are there here. Okay, so how do we create a device? So some of the devices that you're familiar with, we've talked about a MOSFET also in very briefly. For example, you're familiar with the PN junction. So most of the devices will have certain regions which are PE and certain regions which are N. So let's say, so the question that we are asking is, suppose we have a silicon wafer. We have already seen thin crystalline silicon wafer of 400 micron thickness or so, which is p-type, which means that when it is grown, it is already grown with some kind of an impurity, boron impurity, which is p-type. And we wish to create a region within it which is n-type. So there's a p-type silicon, and we want to create a region which is n-type here. And it's written here n plus. The plus means that it's very heavy doping. doping of the order of 10 to the power 19 per centimeter cube, or even 10 to the power 20 per centimeter cube. Very heavy doping here. So you can already see that if I take a piece of silicon and I create an N plus region like this, I'm basically creating a PN junction here. I'm creating a diode at this particular point. And if I make a metal contact here and a contact here, I will get a PN junction, I will get a diode here. Now, the point is that I want an N plus region only here. For example, you may want 2 diodes there. So you may create an N plus here, and you may create an N plus here also. So you'll get one diode here and another diode here. Okay. So you want to create an N plus region selectively in a certain part of silicon. And how do you do that? Well, because you have to do things selectively. And how do you create an N-type region? Well, by adding an N-type impurity, let's say phosphorus. And one way of adding an impurity of phosphorus is through a process called diffusion. So if you take silicon and you have a, let's say, phosphorus in a gaseous form, and if you have high temperatures, the phosphorus will diffuse into the silicon here. But you want to do it only in this region here. So what do? Well, we need to create a structure like this. We need to create silicon dioxide barriers here, right? So we don't want, so what we are going to do is we have silicon dioxide here and we have silicon dioxide here. And if we now diffuse, implantation basically means that you have ions of phosphorus and you accelerate them at high energies, and then they penetrate the silicon here. Okay, so you implant it into silicon. Diffusion is a process which we already know. It at high temperature it will diffuse through the interstitials and spaces that are there in the lattice. They diffuse into the silicon here. So, but we need to create a structure like this, SiO2. Why? Because when we, let's say, try to diffuse phosphorus will not be able to diffuse through silicon dioxide here and silicon dioxide here. It will only diffuse here. So we'll only get N plus in this particular region here. So we need to create this window. And this window or this barrier, SiO2 acts as a barrier for the rest of the region here. So how do we do that? Well, we can start with our p-type silicon wafer and we can oxidize it first. We can oxidize, if you take silicon and you heat it at high temperature in the presence of oxygen, silicon will get oxidized. But you can also deposit a layer of silicon dioxide also. So let's say we deposit silicon dioxide. And then on the silicon surface, we deposit an organic material which we call as photoresist. So photoresist is a material which is sensitive to light. So let's say we're talking about a positive photoresist which undergoes changes upon exposure, and therefore its property changes, and therefore you can distinguish it from a photoresist which has not been exposed. Okay, so we have silicon dioxide, and let's put photoresist on top. So photoresist is put, let's say in the form of a solution, and you can drop a solution and then you can take the silicon substrate and you can spin it at high speed so that the solution covers the entire surface of the silicon wafer here. Now, what we need is a mask. Mask is in simple terms, is a glass plate with certain regions which are opaque, dark, and certain regions which are transparent. So we have a mask, and the mask contains a pattern. The pattern defines where do you want to create an N-type region, where do you want to create a P-type region, and things like that here. So the pattern on the mask, the light and the dark regions, they define the pattern that you want to create in the silicon here. So you expose it to light. So light will not be able to go through opaque regions here. Light will go through this region here. And in this region, the photoresist property will be altered here. While in this region, the photoresist will stay as it is here, because we are talking about a light sensitive material here. So the property of the photoresist is altered, and through this particular process here. So this whole process is called photolithography. And so you can remove, then if you put it in a suitable solvent, you can remove the photoresist from this particular place. Photoresist stays here because it has its original property, but in this case, because of exposure to light, so you can see that this is like a photographic, the kind of process that we use in photography also. So it's similar here. Photolithography is what we call it here. Next, so we can dip the whole wafer in hydrofluoric acid. HF acid etches the silicon dioxide. So what we can do is we can remove the silicon dioxide here from this particular place. And then we can dip it in another solvent and we can remove the photoresist. So thereby we have created a window here. So we have a window of silicon dioxide here. We have silicon dioxide covering the surface here. We have silicon dioxide covering the surface here. Here the surface is exposed. So now if you diffuse phosphorus into it, the phosphorus will go and will create a N-type region here. So thereby you can create an N-type region, and somewhere else if you want to create a P-type region, you can do that. And by that means you can create a device like this here. You can create an N-type region here, you can create an N-type region here, you can create a P-type region here, you can have silicon dioxide here, silicon dioxide here. And we'll see later on this is nothing but the structure of a MOSFET here. So the fabrication is done by, so all the information about fabrication is contained in the mask. The mask contains information about where you want to create P-type, N-type, and all of those, the patterns of opaque and transparent region. It tells where a particular layer has to be deposited here. So the information from the mask is actually transferred to the photoresist through the process of photolithography. And then once you transfer the pattern to the photoresist, then after that you do your various processing steps, diffusion, oxidation, and all of that to create the final device that you're looking for. All right, so that's all for today. We'll continue our discussions and see how diodes and transistors can be made, and then what their properties are and how we can use it to do interesting things in the circuit form. Okay, so let's stop here.